Let's talk about the implementation of our Gauss formulas, okay? So this is our function quad Gauss value. First we fill the table. If using n is 1, then we have the position 0 and we have the weight 2. If we have n is 2, then we have the position minus 1 divided by square root 3 and also positive 1, and the weights are 1, 1. And our example in the last video was the weights were 5 divided by 9, 8 divided by 9, and 5 divided by 9. And the positions were square root of 3 divided by 5, which is 0.6, minus that one, plus that one, and the 0 position. So we fill that tabular here, and then depending on which degree the user have chosen, then we take out for our calculation the line we need. Okay, and then also the user can tell us how many parts does he wish. Does he wish 100 parts? Then he says, okay, n is 100, and so we do that for loop here. And on each part we apply the Gauss formulas. A is the A corresponding to the interval we are dealing with, and B is the endpoint of the interval of that part. And then these are the evaluation points, and these are the function values. And then we apply the rest of the formula. We multiply the function values with the weights, and then we scale by interval length divided by 2. And here we sum up for each part, and so we get our value. And this is our standard code. It's the same as it was always, except of that line. So that's how we implement the Gauss quadrature. And now we want to test how does the Gauss integration competes with the other algorithms, okay? For doing so, we use the code which we also used for testing the Newton-Cotes formulas. And now we again call Newton-Cotes value, but on top we also call Gauss quadrature, and depending on the n, and then with the different degrees, with the different n's, we apply the Gauss formulas. And in the end, we will check our results against the correct results which we got by calling the quad command. And for getting good values, we splitted the integration interval, what is a very good idea. Never forget that idea. If you have a problematic function and you know all the positions of the problems, then always split the integration interval. Okay, let's run that code. And here is our function, constant 1, then a jump, and then this function with a lot of kinks at these positions. And so our correct integration value we get by first integrate from 0 to 1, then integrate from 1 to 1.2, then from this kink to that kink, and so on. This is what we do here. And what do we see? Okay, and this is trapezoidal rule, this is Simpson, and then degree 3, degree 4, degree 5, 6, and 7, and degree 8. These are the results of the Newton-Cotes formulas. And then we apply Gauss quadrature. This is n is 1, n is 2, n is 3, and n is 4. And what do we see? Who is the best of all these algorithms? Okay, this is the best result with n is 3, but this is more or less because the evaluation points are by coincidence somehow the best ones. I think this should not be generalized. What we really see is that Gauss quadrature is not better than the trapezoidal rule. And that's what we set for functions with jumps. And for functions with kinks, the trapezoidal rule is okay, is very good, and all the other algorithms are not really better. If they are better, this is more or less coincidence. The error of all these is more or less in the same range, and also Gauss quadrature is not better than the others. Then take the same function, but the integration interval is starting from 1, so we have no jumps anymore, but we have kings. So let's run that code. This is the function, no jumps but kings. And here is the result. And again, trapezoidal rule is very, very good and is even the best in that line. No, this one is a little better. But apart from that, which is degree 2, 3, 4, degree 5, it's the best of the Newton-Cotes formulas. And how does Gauss quadrature competes? It's not better, not better, not better, and not better. So for functions with kings, the trapezoidal rule is more or less the best integration method. Then our third example, no kings, nothing, a little oscillation. Okay, how does the algorithms compete? Here we have good results for the trapezoidal rule, but even better results for Newton-Cotes with higher degrees. So much better here in this case are the Newton-Cotes formulas with higher degrees. What's about Gauss quadrature? Okay, not better than the best, but the high degree formulas from the Gauss quadrature for this example are very good and can easily compete with the Newton-Cotes formulas. Let's end our test with our fourth function, which looks like that. This is the periodic function exponential of sine of x, and this function is periodic and we integrate one period. And then what do we see? We see that all integration methods more or less produce the same answer. Every method produces a very, very good approximate value, and none of them is better than the others. The trapezoidal rule can compete with all the others in this very special situation. That's a theorem about the trapezoidal rule, that for this kind of functions, periodic function, infinite many, often differentiable, and integration interval is one period, and so the most simple method to integrate in this case, and it can easily compete. Okay, this was our competition, and I hope that gave you a feeling for the different approaches. And now one last point, which I've forgotten to mention in the last, or better in the first video about Gauss quadrature. And this has to do when we started with our Gauss quadrature idea, we had these 6 equations. And we did not know, is there really a solution? We expected, yes, there might be a solution because we have 6 equations and 6 unknowns. But one thing more. The positions x0, x1 and x2, if the solution of this system, the positions are outside of, in this case 0, 1 and later in the interval -1, 1, then we will have a non-satisfying situation because we want to integrate on the interval, let's say -1 to 1, and in this case it will not be tolerable if the positions would lie outside of this interval. So this is also something we don't know in advance, and that's what I say here. But that is true. I should have mentioned that in the first video about Gauss quadrature, but I've forgotten and I wanted to do that in this video. So we are done with Gaussian quadrature.